Hi everybody, this is Dr. Nigro. This screencast is to wrap up our notes section for our new vectors unit. This one's going to focus on right triangles and the trig calculations that we're going to be working with as we use these triangles. All right, so when you're working problems with vectors, you need to start by drawing the triangle that's described in the problem. Now this can take a little bit of practice, so I'm going to be asking you guys to do it for all the problems. But having that triangle is going to help you to decide what trig formulas you need to solve the problem. So we're going to be practicing by filling in this table. All right, now one thing I would suggest is, oops, all right, draw x component first and then draw your y component. That's just going to help us keep our formulas straight. All right, so in other words, draw your x piece first, then draw your y. And once you have your two components, you can add in your resultant. All right, so here's our right triangle. So this is x, this is y, and this is the resultant. All right, so when we draw the right triangle, we're going to start by looking at just a general triangle with no indication of what's being measured. All right, so I'm going to draw a triangle very similar to what I have up there. We've got x and y, right? And when we add those together, we're going to get our resultant vector here. All right, and remember, it's tip to tail, and this is going to give us a right triangle. All right, so if we wanted to calculate what that hypotenuse was, we would use Pythagorean's theorem, where r squared equals x squared plus y squared. All right, if instead we knew the value of the hypotenuse and we knew this angle, which we call theta, all right, then we can use our trigonometry formulas to figure out what x and y are. All right, so if we're looking at a horizontal component, this is going to be x, all right, then I know that the adjacent over the hypotenuse is equal to the cosine of that angle. So the cosine of theta is equal to x divided by r in this case. All right, now we don't often use the formula in this way. Usually we're trying to solve for x. So if I rearrange, x is going to be equal to r times the cosine of our angle. Okay? If instead we're looking for the vertical component, the y component, this should be your opposite leg. Let me put adjacent under here. All right, so that means we're going to be looking over here, right? And that's the sine. So the sine of the angle equals y divided by our hypotenuse, or r. All right, and again, we usually rearrange this so that we have y equals to r times the sine of theta. All right, so we like to set these up so that the opposite is always y and the adjacent is always x. So when I ask you to practice drawing your triangles, that's part of what I want you to do. All right, get used to drawing these in a set way so that these formulas always hold for you. All right, so now we're going to do another triangle. We'll go back up to number 2. All right, we want to draw a right triangle in the center box where the values represent velocity values. So we're going to label our components instead of x and y, vx, vy, and then vr for our hypotenuse. All right, so here we go. This is vx. This is vy, and then our hypotenuse, let's go orange, is going to be VR. All right, again, we've got a right triangle. So if we're going to solve for the value of VR, then VR squared is going to be equal to Vx squared plus Vy squared. So there's Pythagorean's theorem. All right, if instead we're looking for one of the components, all right, we can either look at the adjacent or the opposite. All right, we know that the cosine of the angle is going to be equal to the adjacent, which is Vx, divided by the hypotenuse, which is Vr, or rearranged, Vx equals Vr times the cosine of theta. All right, if instead we're looking at the opposite leg, that's going to be Vy. We know the sine of theta equals Vy divided by Vr. And if we rearrange, Vy will be equal to our hypotenuse, Vr times the sine of our angle. All right, so we would use a triangle that looks like this if we had velocity values in all three spots. All right, now note the formulas are the same from column to column. We're just changing what each leg represents. All right, for our last triangle, let's see, let's go with red. All right, we're going to draw a right triangle in the right box where all the values represent distance values. So we're going to be using dx, dy, and dr for that hypotenuse. Oh, I forgot to put theta in here. I should always put theta in. All right, so here's our horizontal piece. Here's our vertical piece. So we've got dx and dy, and they come together to make a resultant that we're going to call dr. And then there's our right angle, and here is theta. All right, so again, if we know the components and we want to find dr, that value squared is going to be equal to the two components squared. So dx squared plus dy squared. All right, if instead we know the hypotenuse and the angle and we're trying to find one of the components, if we start with our adjacent, we're going to have the cosine of our angle equals dx divided by dr, or rearranged where dx equals the resultant times the cosine of the angle. All right, if instead we're looking at the opposite leg, our vertical leg, that's the sine. So the sine of theta equals dy divided by dr. And if we rearrange that to solve for dy, it's going to be equal to dr times the sine of our angle. All right, so again, we've got three different triangles. This is a general triangle. All right, this one, velocity values, and then this one, distance, or I guess technically displacement. All right, now the one thing to keep in mind when you're looking at these triangles, you can't mix and match. All right, if you have information about the horizontal velocity but the vertical distance, you can't put them both on the same triangle. It's got to be all velocity or all distance. All right, so how do we use these triangles? All right, so we're going to slide down to, I'll do a couple of these with you and I'm going to leave some for you to work on your own. All right, so for each of these problems, you're going to draw the triangle, label the different sides and angles with what is given in the problem. And we got to remember our units. All right, so we're going to draw triangles. So for number one, it says a right triangle has a horizontal leg of 6.8 meters and a vertical leg of 12.1 meters. What is the hypotenuse? All right, so now these triangles don't have to be perfect. All right, we're just drawing some general triangles. All right, so this horizontal leg is 6.8 meters. And this vertical leg is 12.1 meters, all right? And our hypotenuse is going to connect those two right here, all right? So these are both distance values, so we'll be looking for the hypotenuse in terms of distance, all right? This would be our angle theta, and here's our right angle, all right? So this is going to be looking for the resultant. So if we go back up and look at our distance triangle here, all right, we can see that if we want to find the hypotenuse, we need to use Pythagorean's theorem. All right, so we're going to come down here. So dr squared is going to be equal to dx squared plus dy squared. All right, so dr squared equals 6.8 meters squared plus 12.1 meters squared. All right, so if we work our magic with our calculators, we're going to square these two numbers, add them together, and then we have to take the square root of both sides. It's going to be in this ballpark. So we're going to have 192.65 meters squared, and then we're going to take the square root, and we're going to find that our resultant vector has a length of 13.9 meters. All right, so that is this value. Okay? All right, so let's go down and look at one where we've got the angle and the hypotenuse this time. So the hypotenuse of a triangle with an angle of 45 degrees is 81 centimeters long. What are the lengths of the two legs? All right, so in this case, here's what we know. We know that we have a hypotenuse that is 81 centimeters long. All right, and what we're looking for this time are this piece, which is going to be dx, and this piece, which is going to be dy. All right, the problem tells me that this angle theta is 45 degrees. All right, so if we go back up and look, we are again with distance values. All right, this time we're going to be using these two formulas. All right. We know the hypotenuse, we know the angle, so we're going to use our sine and cosine formulas to find those values. All right, so let's try that. All right, we'll start with dy. That's equal to dr times the sine of theta. All right, so in this case, 81 centimeters times the sine of 45 degrees. All right, get out your calculator. Be careful when you put in the sine of the angle. Sometimes your calculator has some operating issues, so make sure you have it in the correct order. All right, I got 57.3 centimeters here. All right, so that will be the length of this leg. All right, we're going to repeat, but we're going to look at the horizontal piece. So dx equals dr times the cosine of theta. All right, so in this case, 81 centimeters times the cosine of 45 degrees. All right, we again plug that into our calculator, and I again got 57.3 centimeters. All right, which makes sense because the angle of 45 is right in between the fully east or the fully north. All right, so it makes sense that my two legs are identical. So this will be 57.3 centimeters as well. Okay. All right, I'm going to do two more, and then I'm going to leave the rest to you. All right, so let's look at number 3. All right, we've got a cannon that's fired upward at a 55-degree angle with a velocity of 75 meters per second. All right, so fired upward, 75 meters per second. All right, and we're going to be, again, filling in the legs of our triangle. So our horizontal piece and our vertical piece. This is a velocity value, so we'll be looking for Vx and Vy this time, and theta is given as 55 degrees. All right, so let's start with Vy. That's the sine, so it's going to be Vr times the sine of theta. So in this case, 75 meters per second times the sine of 55 degrees. All right, so we get our calculators out, we plug in our values, and we find that the vertical component has a value of 61.4 meters per second. All right, do not forget your units here. It's easy to forget them because we're doing all these sines and cosines. But it's still a measurement, so we got to keep them there. All right, so Vx is going to be Vr times the cosine of our angle. So in this case, 75 meters per second times the cosine of 55 degrees. We plug that into our calculator, and we find that the horizontal component, is 43.0 meters per second. All right, so these are the x and y pieces of that triangle that will form that hypotenuse that has a value of 75 meters per second if the angle is 55 degrees. All right, now let's go look at number 4. All right, so number 4, we have a climber working her way up a cliff. If she moves 13.2 meters to the east, then 20.1 meters to the south, what is the resultant? All right, so this time we've been given directional pieces. All right, so we're going to move to the east 13.2 meters, and then we're going to move to the south 20.1 meters. All right, now our resultant is going to be the sum of these two. So it's going to look like this. All right, and since we have distance values, we call it dr. Our angle here is theta. Okay, so this is another Pythagorean theorem problem. All right, we know that the distance of that resultant squared is equal to dx squared plus dy squared. All right, so dr squared is going to be equal to 13.2 meters squared plus a negative 20.1 meters squared. Now, the negative, that's because the y component is down. All right, it's south. All right, now it doesn't really matter in terms of math because when you square a negative number, it becomes positive, but it's probably better to get used to putting in the negative signs when you need to. All right, so once we do the square and then add everything together, we're going to get a value of 578.25 meters squared. We need to square root both sides, and we're going to find that the resultant value should be 24 meters. All right, now it's pointing downward into that southeastern quadrant. So I would also include southeast there. We don't know the angle theta. We could find it, but we don't need to at this point. We'll talk about whether we're going to do that later. Okay, so that gives you 2 examples of each type of problem. All right, there are more problems here. There's 5, 6, and 7. All right, so why don't you give those a try? Although actually, you know what? I think I'm going to work 7. All right, because 7's a little bit different. All right, so a weather report shows you that a tornado was sighted 12 kilometers south and 23 kilometers west of your town. The storm is reported to be moving directly towards your town at a speed of 82 kilometers per hour. All right, so the tornado is 23 kilometers west and, whoops, not 82, 12. Sorry about that. 12 kilometers south. All right, so the tornado is located right here. All right, now it says it's moving towards us. So here we are. We're up here. This is our town. All right, and it's moving at a speed of 82 kilometers per hour. All right, so we have 2 sets of information here. We have some distance values, and then we also have this velocity value. We don't know anything about theta. All right, so the first question is, what distance from your town was the tornado sighted? So we need to figure out dr. All right, we've got dy and dx, so we're going to use those 2 values to find dr. So this is going to be just like what we did before. Dr squared equals dx squared plus dy squared. All right, we plug in our values for dx and dy, and we take the squares of those, and we should get 673 meters squared. We then take the square root of each side, and we find that that tornado is located 25.9 meters to the southwest of our town. All right, so this is where the tornado is. All right, now, how long? Okay, so this is interesting. So this is all about time. All right, so we know that velocity equals distance divided by time. All right, in this case, we know that the velocity of the resultant equals the distance of the resultant divided by time. Please note how I put those R's in there. All right, this is important because you need to match your velocity and distance values on your triangle. You have to use either the resultant for both, or you have to use the x component for both, or the y component for both. For this, I don't know the x and y components of the velocity, so I'm going to use the resultant distance. All right, so time is going to be equal to the distance divided by the velocity. All right, so in this case, we've got a distance of 25.9 meters, and we're dividing that by 82 kilometers per hour. So we got a problem. We've got meters. Oh no, that should be kilometers. Oops, all the way up here, I messed that up. Sorry about that. This should be kilometers to the southwest, and this should be kilometers. So that actually fixes our problem. All right, if we do our division here, that's going to tell us the time in hours that the tornado is going to take the tornado to reach our town. So we've got 25.9 divided by 82. All right, so it's going to take 0.32 hours for that tornado to reach us on its current path. All right, now this one, this addition of time, this is an additional step we're going to start to see more and more often. So we'll talk about this as we continue to work these problems. All right, let me know if you have any questions.